All right, so in this section, we will discuss the fundamental theorem of line integrals. We're not going to prove it, but we'll certainly state it and do a few examples. So before we do that, I just want to sort of motivate, what this is all about using a couple of examples. So the first example, we're given this vector field. So I'm going to use E instead of F, just to give them different names. So E is a vector field, and it's given by xy times I plus x squared plus y times j. And we want to evaluate this line integral right over the curve C, and C is the curve that's joined by two curves, CH and CV, right? So C, what I'm calling C1 here, is, right, it's not a smooth curve, but it's the union of two piecewise smooth curves. And in fact, they're just line segments, right? So you're going from 0, 0 to 2, 0, and then 2, 0 to 2, 4. Okay, so one's horizontal, that's the CH, right? So H for horizontal, and CV, the V is for vertical, right? So that just makes sense. Right, so let's do this, right? The way to do it is to calculate the line integral over the entire curve, we're just going to add the two line integrals, right, for CH and CV. So we'll just have to calculate each one separately, right? So a bit of a nuisance. It makes it a little more tedious, but each one of these is really not going to be that difficult, right? After all, how do you parameterize CH? So that's just going to be, I'll call it RH, maybe. We're just going from 0, 0 to 2, 0. So let's say 2t, 0, right? And then the derivative of that will just be 2 and 0. Right? Yeah, so t goes from 0 to 1, let's say. Right? And then CV, we can parameterize that. We'll call it RV. And here, x will just be 2 the whole way up. And we want to go from 0 to 4, so we'll multiply t by 4. But if we're going from, say, 1 to 2, instead of 0 to 1, then we'll just have to subtract 1 from t. And that should work. And then the derivative of that, prime, yeah, will just be 0 and 4. Okay, so I think we have everything we need here. Right, so to calculate the line integral, the vector field E is x times y, but x is 2t and y is 0, so that's just 0. Right, 2t times 0 is 0. And then x squared plus y, so x squared is going to be 4t squared. Plus y, well, that's just 0, right? And then the dot product with dr is just the derivative, right, which is 2, 0. Right? And that's with respect to t, right? And then plus the vertical part, right? So x times y is 2 times 4 times t minus 1. So that's 8 times t minus 1, or just 8t minus 8, right? And then x squared is going to be 4 plus y, which is 4t minus 4. So 4 plus 4t minus 4 is just 4 times t. And then the dot product with the derivative, 0, 4, with respect to t, right? Okay, so taking the dot products here, we're just going to get 0 times 2, which is 0, plus 0 times 4t squared, which is 0. So, yep, the first integral is, well, just 0. Right? The second one, however, will not be 0. The first component, right, 0 times 8t minus 8 is 0, plus 4 times 4t, which is 16t, dt. Right, and v is going, right, so t is going from, yeah, I forgot to put the t's in here, right? T is going from 0 to 1 in the horizontal part, and then from 1 to 2 for the vertical part. So yeah, we don't need this ch and cv here. We know which ones these are. Okay. In any event, it's just the second integral here, and it's going to be, well, t squared over 2, so that's 8t squared, evaluated between 1 and 2. So 8 times 4 is 32, 8 times 1 is 8, and 32 minus 8 is 24. So we finally get our answer, right? This is just 24. Okay, right, so this is what we did last time. This is nothing new. But, if we didn't do enough examples, here's another one, right? And this is one over a piecewise smooth curve, right? So now I want to do this all over again. Well, not over the same curve, though, right? So I want, for my part B, I'm not going to use red. I'll use... Oh, I'm running out of colors here. Okay, I'll use red. My curve C2 is just going to be the curve. I'll just use the straight line again, but from 0, 0 to 2, 4. And I know that's not straight, but it's going to be tough. Can I connect the dots here? Okay, close enough, right? So this will be my C2. Right, so different curve. It's a straight line, so we can parameterize that very easily, right? So C2 is the line segment from 0, 0 to 2, 4. So we're just going directly there. And so to parameterize that, I guess I'll call it R2. So, right, so t, if we want t to go from 0 to 1, then the x will just be 2t, and the y will be 4t. So that way when t is 1, we'll end up at 2, 4. Make sense? And then the derivative, r2 prime, will just be 2, 4. All right, so again, the key was to calculate the line integral, right, over this curve here, or this line segment. Okay, so we already parameterized r, and so e, what was e again? E was x times y. So x times y here is going to be 2t times 4t. So that's 8t squared. Oops, that's the x component, right? And then the y component will be x squared plus y. So x squared is 4t squared plus y, which is just 4t. Right? So that's the E field. Well, it doesn't have to be an electric field. It's just a vector field, right? So I'm using E for a generic vector field here. All right, and then the derivative of r is just 2, 4 dt, and we're going from 0 to 1. So this is the definite integral from 0 to 1 of 2 times 8t squared, so 16t squared, plus 4 times 4t squared, so that's also 16t squared, plus 4 times 4t is, well, 16t. Right, so 16t squared plus 16t squared is 32t squared plus 16t. Right. So now we just do the integral, right? This is 32 over 3 times t to the 3 plus 8t squared. And now we just evaluate between 0 and 1. So when we plug in 0, we get 0. When we plug in 1, we get 32 over 3 plus 8. But 8 is 24 over 3. So 32 plus 24 over 3 is going to be 56 over 3. Right? Yeah, so 18 2/3, I think. Okay, right. So notice that we're starting at the same point, 0, 0 here. So point A and point B are the same. We're starting at point A, we're ending at point B, right? But we're going along two different paths, right? One, the first path we're going to the right and then up, right? And in the second path we're just going directly there. So sure, there's no reason to think we would get the same answer for both because they're along different paths, right? They're along different curves. Okay. All right, so next example. Okay, so here's our next example, right? So here we're given another vector field. This time I'm calling it f, right? So it's y plus 4 times I plus x plus 2y times j. And again, we're going to evaluate the line integral of that vector field over essentially the same curve that we had earlier, right? The curve is just two line segments from 0, 0 to 2, 0, and then from 2, 0 to 2, 4. So looks like I made a mistake there. That should be 2, 0 right here. And then from 2, 0 to 2, 4. Right, so again, we're dividing it into the horizontal and vertical parts, right? And as before, we just add up the two line integrals. So if we do the one for the vertical part first, t goes from 0 to 1. The vector field here, right, is y plus 4. And y plus 4 for the horizontal part, right, here's the horizontal part, is 0 plus 4, which is 4. And then the y component is x plus 2y. So x plus 2y is 2t plus 2 times 0. So it's just 2 times t, right? And then we take the dot product with 2, 0, and then integrate with respect to t, right? Plus, and then the horizontal part, oh, sorry, I got this backwards. That's the horizontal part, the one we just did. Yeah, you got to do the horizontal first, and then the vertical. Well, I mean, look, we don't, right? We can do the vertical part first if we go up to 0, 4, and then we go to the right to 2, 4, right? But that's a different path, right? So that we can consider that, well, maybe we'll do that after this, right? So that, yeah, so this would be a separate path, a separate curve, say C2. Okay, so maybe we'll do that next. But for now, we're doing the horizontal part from 0, 0 to 2, 0, and then the vertical part from 2, 0 to 2, 4. Okay, so for the vertical part, we're doing from t goes from 1 to 2, and then, let's see, y plus 4 is going to be, well, 4t minus 4 plus 4, which is just 4 times t. And then x plus 2y will be 2 plus 2 times 4 times t minus 1. Okay, so that's going to be, oh boy, so let's see, 2 plus 8 times t minus 1, which is 8t minus 8. So it looks like we get 8 times t minus 6, right? And then the dot product with 0, 4 dt. I think I just made it, right? All right, so now just take the dot products and then evaluate the definite integrals, right? So the first dot product is just 4 times 2, which is 8, right? And then 2t times 0 is 0, so 8 plus 0 is just 8. And then we're going from 1 to 2. T goes from 1 to 2. 4t times 0 is 0. But then the second component, right, that we add to that is 4 times 8t minus 6. So 4 times 8 is 48, right, times t, minus 4 times 6, that's 24. Okay, so when we integrate 8, we get 8 times t, evaluated between 0 and 1. Of course, that's just 8. Yeah, we'll do it underneath, right? And then the second integral, when you integrate 48t, you get 24t squared minus 24 times t. But we're evaluating between 1 and 2. So let's see, when you plug in the 2 first, you get 24 times 2 squared, 24 times 4 minus 24 times 2. Well, that's just 24 times 2, right? Which is 48. And then when you plug in 1, you get 24 minus 24, which is 0. So I think I did that right? It's 24 times 4 minus 24 times 2. Yep, so that is 48. And 8 plus 48 is 56. So I could have done that here, right? 8 plus 48 minus 0. So this is just 56. Okay. And I just realized I made a mistake. All right, so I think it's an easy fix here. It's just arithmetic. So when I did this here, I think this was right? 2 plus 8t minus 8, so 8t minus 6. But that was times 4. And 4 times 8 is not 48, it's 32. So this 48 here should have been a 32. All right, so let's just fix that. Yeah, so 32t minus 4 times 6, so that's 24. So I think that part's correct. All right, and then 32 divided by 2 is not 24, it's 16. So this term here, this should have been a 16. Here, let me highlight that. So that was 16t squared, right? Yeah, half of 32. And then the 24. So that part I think is right too. All right, and then, so both of these numbers, the 48 and the 0, I think are wrong. The 8 is correct, right? The 48 minus 0 is wrong. Okay, so what is that? We plug in 2 for t, so 16 times 2 squared is 64, and then 24 times 2 is 48. So 64 minus 48 is 16. And then when you plug in 1, you just get 16 minus 24. So that's minus negative 8, right? So it's actually plus 8. So 8 plus 16 plus 8 is not 56. So give me a second to erase the 56. Is, of course, 32, I think, right? Yeah, so 8 plus 8 plus 16, 32. All right, so that should be the answer. Yep, again, arithmetic. That's got to be careful of that. I was doing 8 times 6 for some reason, not 8 times 4. So that 48t here over here should have been a 32t. And so that messed up the rest of the arithmetic there. All right, but I think 32 is correct. Right. All right, so that's just part A. Right. So what do we do for part B? Well, how about the curve I suggested earlier, where we go vertically first, CV first, and then CH. And of course, they're not the same C, so maybe, what, should I use a different letter? Should I use D? Right. So yeah, CV, or no, DV. So for that curve, we're just going from 0, 0 to 0, 4. So, sorry. Right. So for R, I guess I'll call this R3, or, no, okay, I'll call it RV, but it's a different RV from before, right? So x is just 0 and y is just 4 times t. I mean, you can make it 1 times t if you don't mind going from t equals 0 to t equals 4. But we can get there in 1 second by just multiplying by 4, right? And so its derivative will just be 0, 4. Right, now for the horizontal part, so now x varies from 0 to 2. So we'll multiply 2 times t. But remember, here we're going from 1 to 2. So we have to subtract 1 from t. So 2 times t minus 1. And then y is just 4 the whole way. So now when we take the derivative of that, we just get 2, 0. And that's from 1 to 2 now, right? Okay, so, so to calculate the line integral over the curve D, which is a piecewise smooth curve, it's just the two lines. So same vector field F. And so again, we have to split it into the vertical and horizontal parts. This time we do the vertical first, and then we do the horizontal. Right, so the first integral will be from 0 to 1, t equals 0 to t equals 1. And let's see, the vector field is y plus 4 for the x component. So y plus 4 here will be 4t plus 4. Right? And that's the vertical component, right? And then the y component will be x plus 2y. Well, x is 0, and 2 times y is 2 times 4t, which is 8 times t. And then multiply by dr, which is 0, 4, times dt. Right. And then we're going from 1 to 2. T equals 1 to t equals 2. So this is the horizontal part, where, x is 2 times t minus 1, or 2t minus 2, and y is 4. So y plus 4 is 4 plus 4, which is 8. And then x plus 2y is going to be 2 times t, 2 times t minus 2 plus 2 times 4, which is 8. So 2t plus 6. And take the dot product with rh prime, which is 2, 0, with respect to t. All right, so we should be able to do these dot products. So 4t plus 4 times 0 is 0. 8 times t times 4 is now 32t. And then the integral from 1, add to that the integral from 1 to 2. We have 8 times 2 is 16. And then 2t plus 6 times 0 is, well, 0. So, right. All right, so 32t, integrate that, you get 16t squared. Right. So that's just reminiscent of, projectile motion, if it were negative 32t, right? And that's evaluated between 0 and 1, right? Plus, when you integrate 16, you get 16t, and that's evaluated between 1 and 2. So we get 16 times 1, which is 16, minus 16 times 0, right? Plus 16 times 2, which is 32. But then minus 16 times 1, so minus 16. So 16 minus 16 is 0, and we get 32 for our answer. So even though we went vertically and then horizontally, it seemed like we get the same answer, right? So yeah, it didn't matter whether we went horizontally first and then vertically, the green curve up here, or if we did the red curve, or the purple curve, right, going vertically first and then horizontally. We get the same answer, 32. Okay, so maybe that's just a coincidence, right? Because notice we went over 2 separate paths here, although it's true we didn't do the vertical one and then the horizontal one. We went directly there, right? We went from A to B on that diagonal line segment. So maybe we should do that here as well, right? So let's do one more path. Let's just go directly from 0, 0 to 2, 4. Okay, So that should be easy because that's just one segment. You don't have to add two separate integrals here. And it's the same parameterization we had before. Yeah, so it's just 2t in 4t. T goes from 0 to 1. All right, so this will be last one, I promise, right? So I'm running out of letters here. So what should we call this curve? I don't want to call it E because that looks like the vector field. How about if I call it, I'll go backwards. How about B? So we're going to do the line integral over B of the same vector field, F, which is y plus 4i plus x plus 2yj. All right, so yeah, we have to parameterize B. So our B, I think we already mentioned, is just 2t for x and 4t for y. And t just goes from 0 to 1. And we need its derivative, rb prime, that's just 2, 4. Okay. So we have the definite integral from 0 to 1 of, so I'm going to forget the vector field here. Oops. So let's just copy that. Oops. I think I erased it, but we'll move it down here. And then I'll move this one back where it should have been. All right, close enough. Oops. Okay. So, right, so y plus 4 down here is going to be 4t plus 4 for the first component. And then for the y component, x plus 2y is 2t plus 8t. So 2t plus 8 times t is 10 times t, right? And then the dot product with 2 and 4. Right, this is the dr part, right? Okay. All right, so let's just do the dot product. It's going to be 4t plus 4 times 2, which is 8t plus 8, right? Plus 10t times 4 is 40t dt. Okay, so we're going to get the integral from 0 to 1 of 48 times t plus 8 with respect to t. And when you integrate 48t, you get 24t squared plus 8 times t, evaluated between 0 and 1. When you plug in 1, you get 24 plus 8. When you plug in 0, you get 0 plus 0. So 24 plus 8 is 32. 32 minus 0 is 32. So look at that, right? It doesn't seem to matter which path we go along. We're getting the same answer every single time here. We're getting 32. Okay. So obviously there's a big difference here between the two vector fields we had. So here's the vector field E, which I will copy that as well. Okay, so we want to compare these two vector fields here. Right. Yeah, so E and F. E was the first one we did. This was in example 1. And the F was example 2. So I'm sorry I got it backwards, but that's what we did in that order, right? So that was E for example 1, and then F for example 2. Right. So yeah, why are we getting the same answer no matter which path we choose, right? And you might think, well, maybe this is a coincidence, right? If I took a really weird path, like along this path here, right, then I might get a different answer. Sure, maybe, right? I mean, maybe this is just a coincidence. Over only these 3 paths, we get the same answer. So without going through, obviously I'm not going to parameterize this really weird curve here, right? But it doesn't matter. You can make a line segment from here to here, and then from here to here. And I promise you, you will get 32, no matter what. Okay? I mean, you know, you can try it. You can do another one, but you should be fairly convinced that it doesn't matter which path you take. The line integral will be 32, as long as we're starting at 0, 0 and ending at 2, 4. Right? Obviously, if we start at 0, 0, and let's say we end at the point, you know, 7, 7, 1, well, we don't have the same endpoint. So then we don't expect to get the same answer, right? All these curves start at the same point. They start at 0, 0, and they end at 2, 4. And that was the case up here as well. They started at 0, 0, and they ended at 2, 4. But again, in example 1, we got 2 different answers for the 2 different paths. And in example 2, we did 3 different paths, and we got all the same answer. So what's going on here, right? So it has to do with the vector fields, right? What's the difference between these 2 vector fields? Well, obviously they're just 2 different vector fields, right? They have different components, different m and n, right? So here m is y plus 4, here n is x plus 2y, and for example 1, m was x times y, n was x squared times x squared plus y. Right. So you might say, well, look, example 1 had x squared, which is not linear, right? You might think m and n for f, those are both linear functions. Yeah, that's not why we get that result, right? It has nothing to do with the fact that m and n are linear here for f, right? Here's what it has to do with, right? Let's calculate the following quantity, right? Partial of n with respect to x minus the partial of m with respect to y. Y, right? You remember when we did this, right? This is when we want to test to see if the vector field is conservative. So let's do this with example 1 first for the e, right? So here, m is x times y, n is x squared plus y. So let's write it out, right? The partial with respect to x of x squared plus y minus the partial of the y partial, the partial with respect to y of m, which is x times y. So you take the 2 partial derivatives, and we get 2x minus x, which is x, right? Which is not 0, right? So partial of n with respect to x is not partial of m with respect to y. So that tells us that in example 1, the vector field E is not conservative. Okay. Well, let's look at example 2, which is the vector field F, right? So again, same partial of n with respect to x minus the partial of m with respect to y, and let's see if we get 0. Or something other than 0, right? Yeah, so partial of n with respect to x. N here is x plus 2y, right? Minus the y partial of m, which is y plus 4. So the partial of x plus 2y with respect to x is just 1, and the y partial of y plus 4 is also 1. When you subtract, you get 0. So that tells me that the partial of n with respect to x equals the partial of m with respect to y. So the vector field F is conservative, right? So that explains why we got the same answer for the different paths, right? When a vector field is conservative, right, the line integral does not depend on the path, right? So that is fairly important here, right? So if the vector field F is conservative, then the line integral does not depend, right? Well, does not depend on the path, right? So let's just say that this line integral is path independent, right? So conservative vector field means the line integrals are path independent. They don't depend on, right, which path you take. They do depend on your starting point and ending point, right? So remember, right, same starting point A and ending point B. Right. Because, yeah, if you take different endpoints, right, so if this is your point A and point B, right, then it doesn't matter how you get there. You can go straight there. You can take a curved path. You can take a really weird curved path here, even one that crosses itself. As long as you end at point B, you're going to get the same line integral, right? But yeah, if you take a different starting point and ending point, say from here to here, right, well, you won't get the same answer, right? You will get the same answer if you take a different path from the same starting point to the same ending point. So I got to call this point C and point D, right? So, yep, at that point, it won't matter how you get there. From C to D, you'll get the same line integrals for all these separate curves. But you'll get a different line integral than you did from point A to point B. Got it? Yeah, so that's what we mean by path independent. It doesn't matter how you get there. As long as you start at one point and end at another point, no matter how you get there, you get the same answer, right? Physically, here's what that means, right? When a vector field is conservative, right, the work done, and remember, work is just the line integral of the force field. It's the work done by the force over that path, over that curve, right? Over your curve from point A to point B. Right. So then the work done is path independent. Okay. Right. So, yeah, so physically what that means is when you have a conservative vector field, it doesn't matter how you get there. Right. So to give an example, let's say we're starting at point A down here. Let's say this is on the ground, and we want to lift up some object to point B over here, right? So say we want to put it on a shelf, right? So we lift this up, right? And we move it over here to point B, right? So we did some work, right? We did some work against gravity to do that, right? And gravity is conservative, right? Right. So yeah, if I lifted this up this high, moved it over here, and then dropped it, it would take the same amount of work. And you might think, wait a minute, you're lifting it up way higher. How is that not more work? Right? So that's a fair question, right? And technically, it doesn't take any work to move it horizontally because gravity acts right vertically. So here, right, here's the answer. Yes, you are. If you just stop here, you are doing more work because you're lifting it up higher. It's a bigger potential difference, right? Right. Moving it left to right doesn't matter. But then you're dropping it. And by dropping it, now gravity takes over. Gravity does the positive work. You're doing negative work, right? Right? So by dropping it, right, you're doing negative work here. And that cancels the work that you did, the extra work that you did to lift it up this much more. But overall, the amount of work done is the same as just lifting it up over this yellow path here, right? Or if you take a different path, let's say you just go straight there and then move it here, no difference in the work done. The line integral or the work done will be the same. Okay? Now, that's only for conservative forces, right? Conservative vector fields, right? If you're on the ground, right, and you take a crate or a box of something and you want to move it horizontally this way, well, we talked about that, right? It's going to take some work to do that. Has nothing to do with, well, has very little to do with gravity, right? It has to do with the force of friction, which is in the same direction. So you're doing work against the force of friction to move it, you know, from left to right, from point A to point B, So yeah, right. On the other hand, right, if you move it back to point A, if you move it backwards now, you're still doing positive work because now the friction will be in the opposite direction. It'll be pointing this way, and you're moving it to the left, right? So you're doing positive work just to move it from point A to point B and then back to point A. Even though you didn't go anywhere, you're ending up at the same point, at the same place, you did positive work, right? As opposed to gravity, where if you lift something up and then just drop it, the total work done is zero, right? Even though you're doing positive work lifting it up, right? Gravity will then do negative work when it falls back down to the ground. So for conservative forces, if you end up at the same place, your total work done is zero, right? So if you calculate the work done, I should use the same color here. If you calculate the work done over a closed path, right, a closed curve, then the net work done, the total work done should be zero, right? So yeah, after all, if you go from point A to point B, and then from point B back to point A again, right, whatever positive work this is, this will be the same but negative, and you'll end up at zero. So zero work when it's a closed path, right? So for a closed curve C. Right. But that didn't happen when we moved the crate horizontally, right? We did a positive net work going right to left and then left to right, even though this is a closed path, a closed curve. Right. And the reason is because, well, friction is not conservative. Right. In fact, it's not even you can't really express it very well as a vector field because, right, it's not a field until you actually move something. So it depends on the velocity essentially. So we won't get into that. So friction, not exactly a good example of a vector field, unlike gravity or the electric force, right? Okay, so let's just make all this official, right? Oh, yeah, before we move on, of course, the vector field E we said was not conservative, right? E was not conservative, right? And so the work done does depend on the path, right? We did a different amount of work going from from 0, 0 to 2, 0 and then up to 2, 4. So that was a different amount of work than going straight from point A to point B. Right? And again, that's not going to happen for, just doing work against gravity. So whatever this E is, this is not a physical, force. It's not something you're going to deal with sort of well, it could be friction, but again, it wouldn't be represented by this nice simple function, functions of x and y. So yeah, if you have a non-conservative vector field, the path that you take will alter the line integral, the work done. And if you go backwards, right, if you go from point A horizontally, then you go up, and then you go back along the diagonal path, right, you don't get zero, right? In fact, what do you get? You get positive 24 minus 56 over 3, which is not zero. In fact, I think it's negative, right? 24 minus 56 over 3. Nope, it's positive 16 over 3. Okay. But the point is it's not zero. So even though this is a closed path, it's a triangle, right? So it's a closed path, right? You don't net the work done to be zero here, right? So yeah, if this is like, let's say you're on a table and this is friction, you move it, first from point A to point 2, 0, then to point B, then back to point A, you did a net positive work, right? It's not going to be zero. Okay, yeah, now we can make this official. Okay, so here was the example that we just did, right? So the vector field F, which if you remember was conservative, we calculated the line integral, that is the work done, right, by the vector field f, over 3 separate curves, right? And here they are again. C1 was the green curve going right and then up. C2 was the purple curve going up and then to the right. And then C3 was the curve going directly there from 0, 0 to 2, 4, right? And we got the same answer each time, 32, right? Okay, so I'm going to show you another way to do this, right? Without having to calculate any of these line integrals. There's a nice shortcut here, right? So remember, we know that this vector field is conservative, right? We showed that by taking partial of n with respect to x and showing that equals partial of m with respect to y, or, you know, we subtracted them and we got 0, but same thing, right? But what else is true about a conservative vector field, right? A conservative vector field, right, has a potential function, right, which I'll call little f. Right. We can find that function, right? Little f, right? So remember what the potential function is. It's the potential function such that if you take the gradient of little f, you get the vector field capital F, right? So, right, and the gradient, of course, is just the two partial derivatives with respect to x and with respect to y. Those are the components of the vector field, right? So to get little f, we just have to integrate the m, right? So we usually call this m and n here. So we integrate m with respect to x, and m is just, well, y plus 4, right? So you integrate y plus 4 with respect to x, and we get x times y plus 4 times x, right? Plus some arbitrary function of y. I'll call it h1 of y. Remember, that can be any function of y because when you take the x partial of that, you get 0. But now we have to do another integral, the integral of n, but now with respect to y. Right? And remember, n is just x plus 2y. But now we take the integral with respect to y. So we get x times y plus y squared, right? Plus some function of x alone, right? And so now the question is, can we make these two functions equal, right? Well, certainly x times y is the same for both, so that's going to be, the function will have to include the term x, y. But notice that this 4x here is only a function of x by itself. So that might as well be h2. So h2 of x, let's just let that equal 4x. And if we do that, then that's going to be the next term, 4x, right? And there's another term, right, y squared, but that's only a function of y. So why don't we let h1 of y just be y squared? And so that'll be our last term for all three of these, right? So xy plus 4x plus y squared. Right. Oh, and don't forget, each of these can also contain a constant, so plus c. C for constant, not for curve in this case, right? So there you go. This is our potential function for the vector field f, which was what, right? It was y plus 4 for m and x plus 2y for n. Right. And so yeah, if we took the gradient of little f, in fact, let's do it, right? So take the partial with respect to x, you get y plus 4, right? And if you take the partial with respect to y, you get x plus 2y, right? Plus 0, the c is constant, becomes 0 in the derivative, right? And this is, of course, just the vector field f itself, right? Yep, same vector field, right? Same m and n. Right. So what does this have to do with the line integral? So, right, so remember, this little f here is essentially kind of like an antiderivative. so to speak, of the vector field capital F, right? Because capital F is a derivative, even though we call it the gradient. The gradient is a kind of a derivative of little f, right? And if you remember, back in Calc 1, you were taught the following. If you take the definite integral from a to b of, let's say, the derivative of f, you can evaluate this definite integral just by plugging in b into f, and then a into f, and then just subtracting, right? This is the fundamental theorem of calculus. I know, that's awfully sloppy, right? So fundamental theorem of calculus. And maybe now you see where this is going. Because remember, we're going to do the fundamental theorem of line integrals. And it's really the same thing as the fundamental theorem of calculus, just, applied to line integrals instead of just definite integrals here. Okay, so here's how it works, right? We have to assume that the vector field F is conservative. If it's not, then we can't do anything. We can't, right? It just doesn't apply. So the vector field is conservative, and little f is the potential function. Well, it could be a function of x, y, and z. So I'll just say little f is its potential function. Right, we're not going to bother with the negative sign. That in a physics course they would write it as a negative, right? Right. So if we want to evaluate, let's say over some curve, the vector field, and if the vector field happens to be the gradient of some potential function, maybe I will write it in terms of x and y for now, but it could be in terms of x, y, and z, I suppose, right? Remember, so this is the dot product with dr, right? So yeah, so the gradient is the derivative. All we have to do is plug in the b and the a. Now, what's the b and the a here? Well, it's the coordinates of the endpoints, right? It's the 2, 4, and 0, 0. So, how are we going to express this? Well, it's essentially, say, x of b, y of b, right? And then minus f evaluated at x of a, y of a. So that's kind of clumsy, but remember, point A just has coordinates xa, ya. And point B has coordinates xb, right, yb. Right, so here's your curve C. This is point A, right? And remember, t varies between little a and little b. So, right, if you have your curve parameterized, right, as x of t, y of b, y of t, and t varies between a and b, you can see why I'm calling this, right, x evaluated at a, y evaluated at a. And then for point B, the coordinates are x evaluated at b, y evaluated at b. Anyways, this, so I think I messed that up here. Let me squeeze that in here now. Okay, that's a little better. Yeah, so this statement here is the fundamental theorem of line integrals. Let me try that again. Okay. Right, so very similar to the fundamental theorem of calculus. The only difference is that the derivative is now the gradient, right? And so your antiderivative is the potential function, little f, right? And we're doing this in 2 dimensions. Again, you can do it in 3. You can have an x, y, and a z, right? But that's all it is. Right. So the easiest way to calculate the line integral would have been just to plug in the 0, 0, and 2, 4, right, into the potential function. So did we calculate the potential function yet? Yes, right here. Let me highlight this in red. This is the potential function. Okay, so I guess I'm going to go up here because I'm running out of space down there. So with that potential function, let's plug in the endpoints, right? Do part B first. Oh, did I do part? Yeah, B first and then A. So plug in the 2 and the 4. So you're going to get, let's see, x times y is 2 times 4, plus 4 times x, which is 2, plus y squared, which is 4 squared. Right, plus c, but we can ignore the c, right? So 8 plus 8 plus 16, right, plus c is 32 plus c. Right. Now we plug in the initial point. We started at 0, 0. That's your point A. So when you plug in 0 and 0, well, right, you get 0 plus 0 plus 0 plus c, which is just c. Okay. Now, remember what the fundamental theorem of calculus says. You have to subtract the two numbers. Same thing with the fundamental theorem of line integrals, right? We have to subtract f of b minus f of a. So 32 plus c minus c is just 32. And if you remember, that was the same answer we got when we calculated all three of these line integrals over the 3 separate paths. We kept getting 32 no matter what. So now, if you didn't believe me before that if we took this path here, say from this point to this point and then back to here, that if we took that line integral over that curve, C4, we would still get 32. Same vector field, same endpoints, just a different path. Right? So yeah, it does not matter which path you take. All that mattered here were the two endpoints, right? Right? The point A and point B. Obviously, if those change, right, then you're, right, these points will change up here. Then you might get different values, of course, right? So yeah. But same initial point A, same endpoint B, then those are the coordinates. When you plug them into the potential function, you just get your answer. So that's effectively the easiest way to evaluate the line integral. Find the potential function, and then plug in the endpoints. Right? Plug in the initial point A and the final point B, and just subtract. Right? In other words, apply the fundamental theorem of line integrals. Okay, so that's it. That's the fundamental theorem of line integrals, and maybe now I can make that official. Right. So here's the official statement from our textbook. Right? It's a theorem, fundamental theorem of line integrals. So C is a piecewise smooth curve. Right? It doesn't have to be one continuous curve here. It can be, say, two pieces. So this will be C2, C1. Again, same point A, from point A to point B, right? Yep. So either way, right, either curve, C1 or C2, right? Right. That lies in an open region R. So this is in some domain, right? Some open domain. It could just be the entire XY plane, right? And R is the curve, you know, the parameterization of the curve from t equals a to t equals b. So here we're starting at t equals a, we're ending at t equals b. Right, and you know, typically 0 to 1 or 0 to 2 or something like that. Right, and F is some conservative vector field. Right, so mi plus nj. Right, and it could have a plus pk. This could easily happen in 3 dimensions. You just add you just add a third component here. Right. So this has to be conservative because otherwise it doesn't have a potential function, right? And then, you know, all of this statement here doesn't make sense. If there is no little f, there's nothing to plug in, right? There's no function to plug those into. So yeah, because it's conservative, that means there is a potential function, lowercase f of xy. So this is our potential. Right, potential energy, potential function, same idea, right? Right, and all that means is that the vector field f is just the gradient, or in the physics sense, it's the negative of the gradient of the potential function. But as I mentioned many times already, we're not going to use the negative sign. It's just for convenience for physics, right? And that's it. So to evaluate the line integral, right, so the key of this is, right, if you want to evaluate a line integral of a conservative vector field f over any curve, right, from point A to point B, right, any curve from point A to point B, you can just find the potential function and evaluate it at the two endpoints, right? Plug in your t equals b, and you have your coordinates of the first point, the final point minus the initial point. Right, so yeah, don't do a minus b, it's f of b minus f of a. Okay. Yeah, so again, very similar to the fundamental theorem of calculus, where the derivative was just, the gradient is just the derivative of a regular function, and then you just plug in, x equals a and x equals b, and you have your definite integral, right? Okay, so yeah, a little more complicated because there's two components or two coordinates, right? Or even three in some cases, right? So this applies when you have, when you have a curve in space as well. So this would happen for xi plus yj, right, plus zk. And then you have a vector field in space, right? So you have mi plus nj plus pk. So the only difference here is that you're just going to have to, plug in a third coordinate for z here. And, it's a little more of a nuisance to find the potential function because then you have to do 3 integrals instead of just 2. But that's all it is, right? So that's the fundamental theorem of line integrals, right? And using this, what we can do is show, oh, I guess I'm out of space. All right, so we can go way back up here now. Right, so I mentioned a few statements that I said earlier that the line integral, right, is path independent. It's an n, if f is conservative. And in fact, this is true the other way. If it's path independent for any path, right, for any curve C, right, then we know the vector field is conservative, right? So it works both ways here, right? But the key is it has to be path independent for any path, right? Not just one or two paths. So in other words, right, this goes both ways. Right. And the other statement I made is if you're going along a closed path, then the line integral will be 0, right, for any closed curve C. Right? So, that could be a circle. A circle is a closed curve, or an ellipse, or any closed curve, right? Closed curve C, and f is conservative. And that's the important thing. If f is not conservative, you may not get 0, right? All right. Yeah, so you can show this just by using the fundamental theorem of line integrals, right? And the way it works is, well, right, if f is conservative, right, we can find the potential function, and then we know that the line integral is just the difference of the two values of the potential function, right? So I'll just say r of b minus r of a, f of r of a, right? And so, yeah, all that matters is the final point and the initial point. It doesn't matter what path, right? And if it's a closed curve, your final point, right, wherever you start, that's also where you end. So if you start on the circle here and you go all the way around, your point A is the same as point B, right? If you're on the ellipse and you go all the way around, point A is equal to point B. If you start here, oh, let's say you want to go around clockwise, you can do that too. Doesn't matter, but your starting point is the same as your ending point. And in that case, when you plug those into your potential function, oh, I got it back. Well, yeah, it's not backwards because it's A in both cases. Of course, you're just going to get 0. So by R of A, what I really mean is, right, the you know, it's a point, right, x of A, y of A. But you can also treat it as a vector too. But you don't plug in vectors into potential functions. You plug in coordinates, right? So a little loose with the notation here. This is a little bit sloppy here. On the other hand, I'm just getting tired of writing, you know, x of b, y of b, minus, right, f of x of a. You can see how sloppy it is. Y of a. So this is my shorthand notation for that. All right, so yeah, just use the fundamental theorem of line integrals, and that's where you get this, right? All right, so that's the key thing for this section, right? That's really, you know, if you have to evaluate a line integral, I would first check to see if the vector field is conservative. And if it is, this is usually the easiest way to do it, right? Rather than actually calculate the, you know, parameterize the curve and then find the, find the vector field in terms of t and then do the dot product and all that stuff. It's, you know, it's work. It takes more work to do it that way, I think. But on the other hand, if you do it using the fundamental theorem of line integrals, you still have to find the potential function, right? And that's doing a couple of integrals and just mixing and matching. Make sure you match, you know, the h1, the h2, and the h3. All right. So yeah, now we can do an actual example here. Okay, so we're given a vector field, right? Y over x squared plus y squared times I plus negative x over x squared plus y squared times j. So it's a vector field in a plane again. We want to evaluate the line integral where c over the curve c. C is just a line segment from 1, 1 to 2 square root of 3, 2. So again, we're just going from point A to point B here. So yeah, from point A, which is 1, 1, to point B, which is, sorry, now I know that parentheses looks like a C, doesn't it? All right, just to make it look a little bit nicer, it's the point B has x 2 square root of 3 and y is 2. All right. Well, right, we have many ways of doing this now, right? We can parameterize this line segment, and again, that shouldn't be hard. It might be a little tricky because A is not 0, 0 anymore, but I don't think that matters a whole lot, right? So yeah, we could do this directly, but I figure we've done that many, many times, right? Let's do it indirectly. Let's take the shortcut here. Well, first of all, you know, right, so what we want to use is the fundamental theorem of line integrals, right? We want to evaluate this line integral not by doing it directly, but by using the fundamental theorem of line integrals. So, right, we have to assume that f is conservative, so it has a potential function, right? And then we can just evaluate that potential function at the endpoint, 2 square root of 3, 2, and at the initial point, 1, 1, and just subtract. Right. Right. Now, of course, this vector field may not be conservative, and if that's the case, then we're wasting time here. We're not going to be able to find the potential function, and there's not, right, we can't plug those points into a non-existent potential function. Right. So yeah, maybe the first thing we should do is check that f is conservative. Right. Is f conservative? And that's a very easy check, right? you just take the partial of n with respect to x and check to see if it's equal to the partial of m with respect to y. Right, so again, this is my m here, and this is my n. And, well, okay, maybe it's not that simple because these are partial derivatives of quotients, so we have to use the quotient rule here. Right. Yeah, on the other hand, if you don't check it, if you just do the two integrals, that should be fine too. So maybe this is a little more work than is necessary. But, you know, it's good practice taking partial derivatives, right? So denominator times the derivative of the numerator. So that's just -1 times the denominator minus numerator times the derivative of the denominator all over the denominator squared. And you've probably done one like this already. So we're going to get 2x squared minus x squared is x squared minus y squared over x squared plus y squared squared. And now we have to do the same thing. The y partial of, this should be y here, of m. M is y over x squared plus y squared. So again, denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the denominator squared. Quotient rule. So we get x squared plus y squared minus 2y squared, which is just x squared minus y squared, right? So yeah, same thing, right? These two things are equal. And so it is conservative. Now we just have to find the potential function, right? Remember how to do that? You just do the integral. After all, the vector field should be, at this point, we know that the vector field is a gradient, right? It's the gradient of some little f, right? So it is a derivative of some potential function little f. Okay, so here we just integrate m with respect to x, right? Don't get mixed up here. When you're taking the partial derivatives, you do you kind of use the opposite coordinate, right? M is the x component, but you take the y partial and so on. But here you just take the integral of m with respect to x, right? So we're integrating y over x squared plus y squared with respect to x. Remember, y is a constant with respect to x, so that can be brought outside. And 1 over x squared plus y squared. So I'm hoping you remember what that is. It's just I think it's just 1 over y times the arctangent of, is it x over y? I think it's y over, yeah, I think it's x over y. Yep. Plus c, except c here is a function, say h1 of y. Oh, and these y's cancel, right? So I think we just get arctangent, I'll say inverse tangent of x over y, right, plus some arbitrary function of y. And when we do the other integral, we should see what that function is. So here we're integrating negative x over x squared plus y squared, but now with respect to y. So it's the negative x that is the constant that comes outside. Right. So when we do this integral, we end up with, let's see, 1 over x times the arctangent. Remember, y is the integral here, so I think we're going to get y over x now, right, plus some function of x. So when we simplify this, we get negative arctangent of y over x, right, plus h2 of x. Okay, so right here was the first integral, here was the second integral, and you can see that this arctangent of y over x is neither a function of only x or only y, it's a function of both, right? So these h's right here are just constants, right? This is just c. But, right, so you might think, but these are different, right? This is the arctangent of x over y is not the same as negative arctangent of y over x. No, they are the same. They are equal. Right? I mean, if you're not convinced, work it out. Right? Work this out here. So, okay. I mean, I'm hoping you don't have to do this, but let's do it anyway. So x over y, let's just give that a name. I'm running out of letters here. How about t? Right? So what is the arctangent? Actually, we don't need the t. Let's just use x over y. That's fine. So what is this? This is some angle. Right? It's an angle of a right triangle. Let's say that's the angle here, whose tangent, right? So if we take the tangent of that angle, we should get x over y, which means x, oh, this is backwards, right? X is the opposite side, y is the adjacent side. Oops. So, okay, just be aware of that you know, that this is backwards here. Or if that really bothers you, how about we do this? We change theta to this angle over here. All right. So theta is, yeah, the angle at the top here. So now the arctangent will be, right, theta. And right, this is still x over y. The tangent of theta is x over y. So opposite over adjacent. Okay. Well, yeah, so what's the negative of arctangent of y over x? It's, again, some angle. I'll call that alpha. Oh, these aren't equal. Oh, my bad. Now I just realized the problem here. Yeah, so if you put the negative on the other side, you get a negative angle, which I guess doesn't really make sense, does it? So what I'm missing here is a pi over 2. So this should be pi over 2, right? So pi over 2 minus the arctangent of y over x is equal to alpha. And alpha is just the supplement, right? It's just this. Yeah, so you're right. They're not equal. But they do differ by just pi over 2, right? So, yeah. So in other words, the arctangent of y over x is going to be pi over 2 minus alpha, right? Which is just theta, which is really just theta here, right? Pi over 2. Oh, maybe I got it backwards. Because the arctangent, if we take the tangent of theta, we don't get y over x, right? We get x over y. So, so what am I trying to say here? This is, oh, this is equal to alpha, sorry, this is equal to theta. Right, so there's no alpha here. This is just theta. Okay, now I think it's right. Right, if we take the arctangent of y over x, right, so now we get pi over 2 minus theta, right, which is what I called alpha here. Right, so if you take the tangent of alpha, you do get y over x. Anyways, it works out. It works out. So, okay, but then where's the pi over 2? Well, that might as well be the c here. That might as well be the constant. Right? So the h2 of x then will just be pi over 2. Right? That'll be our c. Right? So yeah, you get the same thing either way. Right? So the potential function, after all that, is just arctangent of x over y. Or if you want to use, pi over 2 minus the arctangent of y over x, that's fine too. I'll just take the simpler one here. All right. At this point, you might wonder, if I just did the line integral directly here, parametrizing the line and so forth, I would have been done. So yeah, right, we took a lot of detours here. One, we checked that the vector field was conservative. We didn't really have to do that because when we do the when we did the integrals here, we did these, we end up with the same thing, right? And after all, I didn't have to check that these were equal with the pi over 2. But, it's good review of, basic trigonometry here. Yeah. Okay, so now all I need to do are plug in the endpoints, the 1, 1, and the 2 squared of 3, 2. So if we did this right, the line integral, after all this, should just be f evaluated at 2 squared of 3, 2, and then minus f of 1, 1. Did I get that right? Yep. All right, so just take the arctangent of 2 squared of 3 over 2 minus the arctangent of 1 over 1. So this is the arctangent of square root of 3 minus the arctangent of 1. And you should know these by heart, I would hope. I know them by heart, right? I know this is pi over 3 minus pi over 4, which is 4 pi minus 3 pi over 12. So pi over 12. Right. So that was the key step, right? Doing this thing in red here, finding the two integrals and matching them up. They are just arctangent of x over y. And then just plugging in the endpoints and subtracting. Right? So this is what you would have gotten if you just calculated the line integral directly. I don't know, would it have been more work? Less work? Probably about the same. Well, again, with all the detours here, it might have actually been less work at this point, but I don't know. I don't know for sure. I would encourage you to do it the other way, to do it directly, just to get more practice with line integrals. But if you don't want to do that, fine. Just make sure in 15.2 in the previous section, previous video, you get enough practice with calculating line integrals directly. Right? Because after all, in some cases, you have to do it directly. If this vector field here, this given vector field, if this was not conservative, then the fundamental theorem of line integrals simply doesn't work. It doesn't apply. There's no potential function, and then there's no way to evaluate the potential function, which doesn't exist for non-conservative vector fields. So just be aware of that in a lot of cases, there's no other way to do this but directly. But when the vector field is conservative, you might take the shortcut of finding the potential function and then just plugging in the endpoints rather than doing it directly. Okay? All right, so that's the whole idea here. Oh, I guess I want to show you one more thing, which I think is kind of neat, right? This does relate to some physics here. So I want to show conservation of energy, right? Now here energy is just potential energy U plus kinetic energy K. Right, and I know that, so this is really just mechanical energy here, specifically, right? It's not thermal energy, it's not nuclear energy, it's just, straightforward, physics 1 mechanical energy, right? Potential plus kinetic. Okay, kinetic energy, for those of you who haven't had physics, is just 1/2 mv squared. M is the mass, v is the velocity, right? And so v squared is just the dot product of v and v, right? Yeah. So we can write the energy, the total energy, right? This is the total energy. I'm calling this E here, right? And it's a scalar. Energy is a scalar. It's not a vector, right? So the potential energy R just depends on position. I mean, in most cases, right? Certainly mechanical energy does, but yes, you can have potentials that depend on velocities as well, I suppose. Plus the kinetic energy, which I'm just going to write as 1/2 mv squared. Okay, so I want to show that this energy is conserved. Right. What I mean by that is constant. Right. It doesn't change. All right, that if I take the energy at a specific time, say T1, and I take the energy at a different time, T2, that those would be the same, right? So yeah, on the other hand, I could do this, right, for any T1 and T2. It's probably easier if I just take the derivative of E with respect to T. Right? If it's truly constant, then the derivative should be 0. Okay, so let's do that. Let's take the derivative of E with respect to T, and let's just take the derivative of both sides, right? So the derivative of U of R is the position function, right? Plus 1/2 mv squared. All right, so this is familiar. You're just going to take the derivative of U of R, right, plus the derivative of 1/2 mv squared. Now, 1/2 m is a constant, so we're just taking the derivative of v squared, if you like, right? Right. So here, though, because u might be a function of time, but it's only indirectly, only because r is a function of t, right? So yeah, maybe I should make this more explicit, right? R, the position, of course, will depend on t here. So this is r of t. So this requires the chain rule, right? We're taking the derivative of u with respect to r, right? The derivative of u, well, that's really just the gradient of u with respect to r, right, as a function of r, right? Dot product, the derivative of r. Right? That's the chain rule. Right? So this is by the chain rule. Right? And then plus, so I had that plus in the wrong place here. Again, the 1/2 m is a constant, so m over 2 if you like. And remember, this is velocity. This is v dot v. Right? V squared is just v dot v. Right. So we still have the gradient of u, right? Dot product with the derivative of r, well, that is the velocity. Well, I'll just call that v, right? Plus m over 2. And you've done this before, right? This is just v dot the derivative of v plus the derivative of v dot v. So there's two of these. And right, so then we just cancel. Oh, hang on, right? So the gradient of u dot v plus, and then we cancel the 2's, right? So this is m of v dot the derivative of v. The derivative of v is the acceleration, a, right? Okay. Yeah, let's keep going, right? So that we still have the gradient of u. Well, we know what that is, right? That's just going to be the force dot the velocity plus, and remember, the m can go with any constant here. I'm going to pull the m with the a, and then just take the dot product with v. Okay, so remember, in physics, right, the force is the negative of the gradient of u, right? So this is going to be the negative of the force dot v, right, plus ma dot v. So I can factor out the v here. This is minus f plus ma dot product with v. But even if you've only had basic physics, you probably remember that F equals ma, right? This is Newton's second law of motion, which means if I take F minus ma, I just get 0. Or I do it the other way, right? ma minus F, which is what I have over here. Negative F plus ma, right? That has to be the 0. Oh, sorry, 0 vector. So, yep, this is just the 0 vector dot v. V dot 0, anything dot 0 is 0. Right. So what did we just show here? We showed that the derivative of e is 0, which means, right, e is a constant. E is conserved. The energy is conserved. Okay, so again, I think that's pretty neat that you can show conservation of energy. But notice that we relied on this one very important object here, that the force is the negative of the gradient of u. In other words, right, that the force is conservative. Right? And in that sense, well, if the force is conservative, of course you conserve energy, right? And so maybe this is somewhat of a tautology here. If the force conserves energy, then energy is conserved. If energy is conserved, then the force is conservative. So we really didn't really show anything, we didn't already know. But again, I think it's still a pretty neat calculation that you do get 0 for the derivative of E, for the derivative of the energy, just showing that the energy is a conserved quantity. It is a constant of the motion. It does not change over time, right? Your potential energy might change, right? If your potential energy increases, then the kinetic energy has to decrease by the same amount. So this is one of the main pinnacles of physics is conservation of energy. Right? Total energy is always conserved, right? Over a closed system, blah, 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 right? So if the universe is a closed system, then the energy is conserved, right? If you have a box that's totally insulated, isolated from the rest of the world, then whatever happens inside the box, things move around or whatever, right? Whatever happens inside, the total energy inside will be conserved, right? Now, if the box can leak energy, then that's another matter. Then you have to take into account the box plus the environment. But now we're getting into physics, so I wanted to show the math of the conservation of energy. Assuming that you have a conservative force, you can show that the energy is conserved. Right? Okay, so that's it for this section here.